Hi, welcome to another lecture in the NPTEL course on Haskell. In the previous lecture, we looked at binary trees. In this lecture, we will add more structure to binary trees and study what are called binary search trees. So, in the slides, I have repeated the whole derivation of creating a binary tree and the linear time version of it. Let me skip past all these and let's get to binary search trees. Okay, and binary search trees are very important because you can think of binary search trees as contributing towards creating a set ADT. Recall that ADT stands for abstract data type. Okay, and you can think of binary search trees as one way of uh, implementing a set abstract data type. What are the kinds of set or dictionary? There are various of these collection data types which are implemented using smart strategies, using trees, heaps and so on. But to a user, they are just sets. You can add elements to a set, you can remove an element from a set, you can search for the presence of an element in a set. Okay, so the set ADT to begin with, we will try to support these operations: insert into a set, delete from a set, and search in a set, search for an element in a set. And you might also have some auxiliary functions like from list, which will these are utility functions which will turn a list into a set. And the most straightforward implementation might be that you create a module called set and then you do these things, export the recall that exporting the type constructor without exporting any of the value constructors. Right, so that's what that does. Insert into, delete from, search from list. Okay, these are all other functions that you want to export, and your set itself is just maintained as set is a, remember this is a type constructor, that's a value constructor or a wrapper really. It's a wrapper around just a list. Okay, you can maintain a set as a list. And in this case, as it so turns out, you can also you could have made this into a new type instead of data, because there is only one constructor and that constructor has only one argument. Okay, and here is how you would implement these various functionalities. Search in a set is now just a search in a list. You are invoking the elem function. So, you are asking whether x is an element of x's. Insert into is just if x is already an element of, let us say that we will maintain only distinct elements in the list. Right. So, insert into is just saying if x is an element of x's, then x's, otherwise x colon x's, you are just putting it at the front and you are putting the wrapper outside after all this. And also remember that most of these functionalities you can do only if A admits equality. A should admit equality checks, the type A. Okay. Okay. So, delete from x is nothing but filter not equal to x from x's. All elements not equal to x you retain, and if x is there you throw it away. From list is just set.nub. Nub recall uh, removes all duplicates from a list. right? So you do num on a list and then you apply the set constructor on top of it, and that's what you have from list. You could do this. Let's check how much time it takes. Search takes order n time, because in general you do not know whether the element is at the very beginning or at the very end or not there at all, and if the element is not present in the list at all, you have to anyway go through the whole list. Insert into again takes order n time, because even though insert into only does x colon xs, it checks for the presence of x, and it checks whether x is an element of xs. Right, it checks whether x is an element of xs beforehand. So this is not that will take order n time. Delete from also takes order n time, because you are filtering throughout the whole list and retaining elements not equal to x. You have to go through the whole list. So a sequence of n operations, no matter what operations they are, will take order n squared time, unless you try to keep on deleting from an empty list. Okay, fine. So we can do better if the elements admit an order. So and that is what we are going to see now, how binary search trees are a way to implementing the set ADT. And here for binary search trees, you will assume that the type of elements admits an order, or in other words, A is an instance of ORD. In that case, I can create BST of A. Okay. So binary search tree is a binary tree, stores values of type A such that A is an instance of ORD. In a binary search tree, values in the left subtree will all be strictly smaller than the root, values in the right subtree will be strictly greater than the root, and recursively the left subtree and the right subtree will themselves be binary search trees. Yeah, so in general I'll have a node like this, node TLXTR. So pictorially you will see that x is the root, everything in TL less than x. Everything in TR is greater than x. Okay, that is the idea in a binary search tree. Here are some examples. 3, to the left you have 1, 2, and 1 and 2 are less than 3. To the right you have 4, 5, 6, which are greater than 3. Go to the left subtree, 1, to the left there is nothing, to the right there is 2, so this is fine. This whole part is fine. Go to 5, to the left there is 4 and to the right there is 6, so this whole part is fine, this whole part is fine. Here you have another binary search tree, 4, to the left is 1, 2, 3, to the right is 5, 6. Go to the left 2, to the left there is 1, to the right there is 3, so this is okay, this part is okay. And go to the right 6, you have, to the right there is nothing, to the left there is 5, so this part is okay, this part is okay. Here are some non-examples, 3, 2, 4, 6, 5, here there is a violation. Four is greater than 3, but 4 is occurring on the left subtree, right? So that's already a violation. Here there is no violation at the root, because 2 and then there is 0, 1 on the left and 3, 4, 5 on the right. Go to the right, 4, there is 3 on the left and 5 on the right, that is also okay, but here there is a violation. Okay, 1 is greater than 0 but lies to the left of 0. That's a violation. So those are examples, these are non-examples of a binary search tree, even though these are all binary trees. Now how do you represent binary search trees in Haskell? Nothing at all. You had earlier B tree of A, now you do BST of A, that's it. There is no more change that is needed. This is what you do. And there are various utility functions you can have. Empty BST is just nil, so this is a smart constructor if you will. And you can check whether the tree is empty of nil is true, is empty of anything else is false. This is exactly the same routines that we had for B tree, you can lift it to BSTs. Okay, here is an important point. Just because you named something a binary search tree doesn't mean that, just because you named a type BST doesn't mean that element of BST are actually binary search trees. Okay, so I could very well do a totally non-binary search tree and it will still type check. I will show it to you in a minute when I go to the VS Code. But one of the things that you might want to do is to check whether a BST is a value of type BST is actually a binary search tree. And one way to do that, so this is the importance of binary search tree and this is the importance of in-order that we talked about earlier. So if you have a binary search tree, what can we say about in-order T? Okay, recall that you have X here and then you have right, and recall what in order does, it will first list everything in the left subtree, then it will list X and then it will list TR. So everything in order TL, so if I do this, and then X, right, I am doing in order TL and then X and then TR, this is my list. Everything here is less than, everything here is greater than X. So it is almost like sorted order. Suppose the left, suppose this were sorted, in order TL is sorted, and suppose in order TR is sorted, then the whole thing is sorted. It's almost like the quick sort thing that we saw. If in order TL is sorted and in order TR is sorted, then in order T is sorted. But in order TL, by recursion you can show that that is sorted because its left subtree, if its left subtree is sorted and its right subtree, the in order is sorted, then in order TL itself will be sorted. You keep on going all the way down till you come to the leaf level, till you come to a place where you have nil, and nil is just empty list, so that's by definition sorted. So you can actually prove by induction, on structure of trees or size of trees. What can you prove by induction? This is the statement that you can prove. Right? If T is a binary search tree, then in order T is sorted, and vice versa also. If in order T is sorted, then T has to be a binary search tree. Yeah, these things you can prove. In fact, I will not say this. T is a binary search tree if and only if in order T is sorted. So one way of checking whether an arbitrary B tree is a binary search tree or not is to do in order and then check whether the in order listing is sorted. How do you check whether something is sorted? This is one way of doing it. Is sorted of empty list is true. Is sorted of excess is that you will take excess, you will take tail of excess, right, and then tail of excess is right, that is tail of excess, but then you can do zip width of x's and tail of x's with less than or equal to, which means that, so if I have my list like this, I am comparing this with this. I am comparing the first element with the second element with the third element with fourth element with fifth element. I am doing these comparisons and checking whether less than or equal to holds between these things. So if less than or equal to holds for everyone, then it means first element is less than the second element is less than or equal to the third element, etc., etc., etc. So now zip width of this will provide a list, we will produce a list of booleans, and if the list is actually sorted, then I will have a boolean list of booleans where every value will be true, 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 and is a function of type list of bool arrow bool. And what it will do is it will take the AND of all. If everything is true, it will be true. If even once is false, if even one of the entries is false, it will produce false. Okay. So in this way, you can actually check whether a list is sorted or not. And to check whether an arbitrary element of type BSTA is actually a binary search tree, you can do this. Okay, fine. If T is a BST, in order T is a sorted list, and also vice versa. Okay, so let us go and see how some of these things are programmed and run a few examples. Right, I have BSTA, yeah, is nil node BSTA A BSTA deriving EQ. Yeah, earlier I didn't have access to EQ, etc., because B tree of A is just any tree A. I can always put any element, any collection of elements in some tree format. But now we want to insist on something like, yeah, even earlier I could have done deriving EQ, that is equality checks between T1 and T2, but then that would assume that elements of the B tree admitted equality. Now I know that in the case of a BST, I am going to work only with elements that admit an order, so therefore I can do this deriving EQ. Yeah, this is possible. Okay. Now empty BST is just nil. Yeah, empty BST is just defined to be nil. Is empty is just doing the same thing. Is empty nil is true, is empty anything else is false. In order is go of empty, where go of empty list, where go L nil is L, go L node TL XTR is go of X colon go LTR TL. This is the same as the earlier go that we saw, except for in order, except that I have switched the order of the arguments. So shouldn't be much of an issue. Though this order makes it a little awkward to parse this expression, so maybe I should do the following. Okay, fine. So go nil L is L go node TL XTR is you do go of TL on X colon go of TRL. Okay, this is something that you already seen. And here is BST. Okay, so here is a more naive is this thing. This is a more straightforward is sorted routine. Without resorting to zip width and whatnot. So to check whether a tree of type BSTA is actually a binary search tree or not, I do in order and then I check whether it is sorted. Okay. Now, actually, to just tell you why it is important to have this BST, let's go here. I have GHCI. Let me load. Okay, I have loaded this this particular program file, and actually you can say a create tree. So there is no create tree. Okay, so what you can do is you can actually say that let's just check node. Let me create a couple of binary search trees here. I will deliberately violate this thing. So node. Okay, this example is enough. I don't need a tree too. Okay, so I have declared tree1 to be a BST of int. So now let's do tree1. Notice that I have 2 as the root. To its left there is 0, 1. But here there is a violation of the binary search tree property, right? I have 0 whose left child is 1. That shouldn't be the case. This is fine. 4, its left child is 3 and its right child is 5. This is a non-example. This is actually not a binary search tree, but I am able to give type BST to this. This just tells you that I can call a type whatever I want, but whether it has the semantic, whether it has the properties that I want it to have is a question mark, right? Which is why if I now say is BST of tree1, I will get false. Why? Because I could do in order of tree1 and that will be 1, 0, 2, 3, 4, 5 and that's a problem, right? Because I want it to be 0, 1, 2, 3, 4, 5. Okay. You could create, let's try to create a random binary search tree and let's see whether it is actually a binary search tree. Access is randints 25 elements, let's say, and let's see what is xs. Xs is really some random list minus 138 plus 116 etc etc. And now if I say from list R, let's say, okay. So the issue is that I need fewer elements, let's say 15 elements, okay, and then I could do from list L. Okay, here is a binary search tree, right? Because you look at this, the root is 91, to its right there is 137, 163, to its left every element is strictly less than 91, and here it's 55, to its right there is 67, 77, but to its left every element is less than 55. You have 45 here, and there are all these negative numbers, and recursively you can check just from the picture that the binary search tree property is being followed, okay. But you could also ask, is BST right, and it says true. This is not the only binary search tree you can create from these elements. From the same XS I can create another binary tree also from list R XS, and that's this, okay. So it is a question of whether you want to process elements from the right of the list or from the left of the list. Here I am trying to process it from the right of the list, and now you see that instead of having 91 as the root, you have some minus 25 as the root, and to the left are still elements less than minus 25, and to the right are elements greater than 25, and so on. You can check that visually that this is also a binary search tree, okay. Okay, so now we have seen how to we will see how we did this from list itself in a bit. We have now seen how to check whether whether an element of type BSTA is sorted or not, is actually a binary search tree or not. Let's look at the three most important operations that you want to do on a binary search tree. Remember that we said that binary search trees are supposed to implement the set abstract data type, and set has insert into, delete from, and search. So we have to have ways of inserting into a binary search tree, deleting from a binary search tree, and searching in a binary search tree, okay. And I will show that in the slides next, and once I have discussed all the programs, I will come back to VS Code, okay. Now before we do all this, we have a few more utility functions which are quite useful. I want to find the minimum in a tree, the minimum value in a non-empty tree, okay. Now actually if you think about it, if T is a binary search tree, min of T is the leftmost node. I wouldn't say leftmost leaf, I should say leftmost node. Why? Because I might have 0 and then let's say 20. Left subtree is nil, no left subtree. And I have some tree here, but I know that everything here is greater than 20. So the minimum value is at the root. But if there is a left subtree, but root is also the leftmost node, if you will, because everything else is in the right subtree. So in that sense. But if there is a left subtree, suppose I have 20 here and I go here, there is some root, let's say 10, and there is some left side and left subtree and right subtree, and the left subtree is minus 20, and then there is some left subtree and right subtree, and at this point it is minus 30, and there is no left subtree here. Now what can you say? There might be a right subtree to this minus 30, but all those will be greater than minus 30. There will be a right subtree to this minus 20, all those will be greater than minus 20. There will be something to the right, all that will be greater than 10, all that will be greater than 20. So in any case, the leftmost leaf. So I can say min of T is the leftmost node again. right? Because you go 20, 10, 20, minus 20, minus 30, minus 30 might have a right subtree, but you are ignoring all that, okay? You keep going, so, or in other words, you keep going left, left, left till you cannot go left any further. That point, that is the minimum element. But remember, this is only the minimum element in a binary search tree, but values of type BSTA need not be a binary search tree, okay? So, in general, if I want to find the minimum in a binary search tree, I need to actually think of it as finding the minimum in some tree where nodes can be compared. That is all I know for now, okay? And what is the minimum? I will have X here and I will have a left subtree and a right subtree. Suppose inductively I find recursively I find the minimum of TL, call it Y. Recursively I find the minimum of TR, call it Z. But there is a problem, your TR could be empty. If the TR is nil, then there is no minimum element, there is no element at all. What to say about minimum element? If TL is empty, again there is no element at all. So, but you know that there is some element in the tree, namely X, okay? So, here is what you do. Min in a tree of node TL X TR is min of X and min YZ, where Y, if is empty of TL, if the left subtree is empty, then you take Y to be X itself. Otherwise, it is min T of TL. The right subtree is empty, then you take Z to be X itself, otherwise you take it to be min T of TR. So, now you have 3 elements. In the worst case, all 3 elements could be X, in which case the minimum will be X, but otherwise it will be different elements, in which case you will pick the smaller of the 3 elements, right? So, that is the thing about min T, okay? So, you are essentially comparing all elements in the tree, and the time taken for this will be order n. N is the size of the tree. Because you have to compute the minimum of the left subtree, compute the minimum of the right subtree, that is 2 recursive calls on trees of size NL and NR, and then finally you have to do some 2 comparisons. So, you can actually work out recursion and find the number of steps taken, the number of comparisons taken would be 2n or some such. Okay. Max T is similar and you use max instead of min.